in addition to running a program and profiling it on a real machine, it's sometimes very useful to use a simulator of some kind. Valgrind, I pronounce it like that because Val refers to Valhall of Nordic mythology. Okay, Valgrind, it emulates the program and it can collect more statistics. Usually it is only interested in finding memory errors, but and that's the default tool, which is not required to write like this. But there are several different tools, including one to observe cache misses. So this Cachegrind, it counts the number of instructions executed and the number of read and writes, and then we can see I1 and D1 and L2. The cache is, there's multiple caches in this model, and there is one instruction cache and one data cache, and this at the first, I mean with the one here. So they are the smallest and fastest. Instruction cache, there is only one, and the data cache, it's usually only one, and then the L2 cache, that's a cache which contains both instructions and data. So that's called a unified cache. But what's important here is we can see how many cache misses there are, and this is very useful before thinking about how we should improve the cache behavior. If it's already very good, there is no point in doing it. And I really recommend that you should run this tool on int_opt before you consider how to improve the cache behavior. You can probably guess without running this tool the result. But I won't spoil your evaluation of that. But it's a good idea to check this first. What we can see here is the number of reads and writes, and which of these we gave resulted in misses. Okay, so in summary, first write a correct version. And then if your program already is sufficiently fast, then there's no point to improve it, probably. And then we need to understand why. I mean, if it's not sufficiently fast, we need to understand why it isn't. That means figure out first, what is it that takes time? And second, how can we improve the situation? And just guessing or thinking that it's probably that, it's only in a very basic situation where that can be useful. I mean, if you know that you have used a very bad algorithm for some part of a program, then maybe that's a good idea to start. But really, it's better to first run a profiler to check what actually matters in the program. Guessing which part takes most of the time is really not so easy. Okay? And the profilers can give you very, very detailed insights of what happens. Also, if you don't understand why a certain function takes most of the time, then read the assembly code. Maybe there is something that reveals why it's slow. For instance, maybe you have mixed int and float, or int and double, and there are lots of unnecessary conversions between floating point and integers, and vice versa. And that can be found in the assembly code. Sometimes Cachegrind can give you very useful information about cache misses, and there are options presented in the book so that you can see which line has a certain number of cache misses. But it does not tell you why there are cache misses. I mean, suppose you get the cache miss to variable x. Cachegrind will not tell you which other data overwrote x in the cache. I mean, caused x to be replaced and forgotten by the cache. And the profilers, they certainly don't either. So what one can do, if one really cares about the performance, is to take a simulator or write a new one, but that usually takes some time, and collect this information on your own, and see which variable actually caused the replacement of something useful. Now, Cachegrind, in general, Valgrind, it's approximately 100 times slower than running on the real machine. The memory sanitizer, it was measured for a certain set of programs. It was 76% slower than on the real machine, so that's really much faster. And Valgrind, that's a relatively fast simulator. But in general, simulators are usually much slower than real machines. On the other hand, simulators, they can count the number of clock cycles exactly, so you don't have to run them for more than 1 or 2 iterations of a certain loop. So you don't have to run it for 5 minutes to get good statistics. Instead, you can run it 1 iteration or 2 and see that this loop takes, for instance, 44 clock cycles to execute. Okay, and then if you don't understand why it takes 44 clock cycles, which I mean usually one does not without looking at what happens, then you can use the IBM if you have a power machine, and you can use the IBM simulator to visualize what happens in the pipeline, so you can see exactly what happens and can see why it takes. I mean, it's not interesting that it just that it was 44 or not 40 or 46 or something like that, but exactly what happens. That's can explain more about your program. So to run just this simulation for 1 or 2 iterations can be actually much faster than running on a real machine. So depending on how this simulator is written, this is very quick to do. I mean, the simulator is it's a functional simulator about what happens in the pipeline. It does not simulate at the semiconductor level, of course, because then it can take much. I mean, that's also interesting, but not for performance analysis. It's interesting for other situations which are not related to this course.